All right, new section. So in this section, we're going to talk about parameterization, which is kind of a fun little topic. The way I think about parameterization is typically when you're trying to graph something, you're given a single equation, like y equals 1/2 x plus 2, for example. And that equation ties together your x variable and your y variable. And what you want to graph are the series of points so that when you plug in the x coordinate for x and the y coordinate for y, you get a true equation here. And because of the form of the specific equation, we kind of know what it looks like. It's in the form y equals mx plus b, so we know it's linear. Playing the role of the b is a positive 2, so we know the y-intercept is at 2. And then the slope is 1/2, so we know that rise over run is 1/2. In other words, it goes up 1 unit each time it goes to the right 2 units. And I guess something that looks more or less like this. Here's the graph of y equals 1/2 x plus 2. And it's not just linear equations that we can graph. For example, we can tie together the y and the x coordinate in this way, where y is equal to the square of the x coordinate minus 3. And maybe you recognize this is our standard parabola shifted down 3 units. So some of the points that satisfy this equation are outlined in green here. And if I do my best to sketch a curve, it looks more or less like this. Y equals x squared minus 3. And you're like, yeah, I know how to graph lines, and I know how to graph shifted parabolas. What's this have to do with parameterization? Well, the idea for parameterization is there's another way we can come up with graphs like this. Rather than having a single equation that relates together the x and the y coordinate, like we see in red here or in green here, I can have two separate equations, one that tells me what the x coordinate will be, and one that tells me what the y coordinate will be. Up here I have two separate examples in red and green. Down here I have two equations, but it's just a single example because when you're parameterizing a curve, you have two equations, not just one. One equation tells you what the x coordinate should be, the other equation tells you what the y coordinate should be. They're not tied together by a single equation. I don't have the x's equal to the y's. The x's are a function of some variable, typically we choose the letter t, and the y's are a different function of that same variable, t in this case. I think the easiest way to think about it is think about we're tracking the position of something over time. So that's a big advantage with parameterization as opposed to just having these curves. There's no notion of time here. This is just the series of points that satisfies this equation. But by changing from one equation to two equations, we can introduce a new variable, time, and then we can kind of think about movement along a line as opposed to just the line itself. Let me show you how it works. Suppose we had these two equations, x equals negative 1/2 t plus 3 and y equals 2t minus 1. And you want to know what graph is described by these equations right here. Again, it's just a single graph even though there's two equations. We still have our x-axis and our y-axis. And probably the easiest way to get an idea of what the graph looks like is figure out what the x-coordinate is at some time, and then figure out what the y-coordinate is at that same time, and that'll give us a point at some time. So maybe I'll keep track of time, and then also the x-coordinate and also the y-coordinate. Tracking the movements of a particle is a typical application for parameterization, so maybe we'll pretend that's what's going on. I want to know where the particle is located at time 0. So what I do is I plug in 0 into this equation to figure out the x-coordinate of the particle. Negative 1/2 times 0 plus 3 is just equal to 3. And then I plug in 0 for t into this equation. 2 times 0 minus 1 is equal to negative 1. What that tells me is that at time 0, the particle has an x-coordinate of 3 and a y-coordinate of negative 1. So the particle is right here when t is equal to 0. Nothing special about time 0. I can do that same thing for time 1. If I change all the t's into 1s, I get negative 1/2 times 1 plus 3. In other words, 2.5 for my x-coordinate. And if I plug in 1 over here, 2 times 1 is 2, minus 1 leaves me with 1. What I'm saying is that at time 1, the x-coordinate should be 2.5, and the y-coordinate should be positive 1. Here's where the x-coordinate is 2.5. Here's where the y-coordinate is positive 1. Here's t equals 1. What about at time 2? Same logic, plugging in 2 for t here. I get negative 1 plus 3, in other words 2. Plugging in 2 for t here, I get 4 minus 1, so I get 3. At time 2, the x-coordinate is at 2, and the y-coordinate is at 3. You may notice that the x-coordinate as a function of time is linear here. Think y equals mx plus b, except the x is playing the role of the y, and the t is playing the role of the x. It's linear with the slope of negative 1/2 and a y-intercept of 3. So when t equals 0, the x-coordinate is equal to 3, and then each time I add 1 to the value of t, my value of x decreases by 1/2. So at time 3, this would have ended up being 1.5, and at time 4, this would end up being 1. And I can work backwards to figure out at time negative 1, my x-coordinate would have been 3.5, and at time negative 2, my x-coordinate would have been 4. Same logic for the y-coordinate. This is of the form y equals mx plus b. The y is playing the role of the y, but the t is playing the role of the x. The value of b is -1, which tells me that at time 0, the y-coordinate is -1. And the value of m is 2, so each time I increase t by 1, I have to increase this value by 2. Adding 2 gets me to 1, adding 2 more gets me to 3, adding 2 more would get me 5, 2 more would give me 7. Same logic working backwards, this would be -3 and -5. I can plot more of these points if I want, although pretty quickly I get outside of the graph that I have. And then I can connect these points with a straight line, and I've got my graph. You might look at this and be like, whoa, that was super complicated. Wouldn't it be a whole lot easier to describe this line in the form y equals mx plus b? Just figure out what the y-intercept would be, some value way up here, figure out what the slope is, and then you have this line? And the short answer is yes. For this specific graph, it would be a lot easier to come up with the graph by writing the equation in the standard form as opposed to the parameterized form. However, just because it's easier doesn't necessarily mean it's better. There's a lot of advantages to the parameterized form. One specific advantage is we get to include this extra dimension, this notion of time, which can be really useful. In fact, it'll turn out that that's the biggest advantage, I think, of parameterization, is it allows us to add this concept of movement because we're tracking time. But that's not the only advantage. Another advantage is that parameterization gives us a lot more freedom. If you kind of think about this equation, we only have a single equation that ties together the x and the y variable, so there's not that much we can do with it. But when we have two separate equations, we can get really creative in terms of what happens with the x-coordinate and really creative in terms of what happens with the y-coordinate in a way that maybe we wouldn't be able to come up with, not easily or perhaps not at all, if we were writing the equation in the standard form. But that's all stuff we'll get into in future videos. The idea of this video was just to introduce this idea of parameterization. I like to think about it as a new way to describe a curve. Instead of one equation that relates together the x and the y coordinate, you get two separate equations, one describing the x, one describing the y. To make sure that's all making sense, let me give you another parameterized equation here. X is equal to t squared minus 2, and y is equal to 5 minus 3t. What I'd like is for you to be able to come up with the curve that these parameterized equations represent. You might want to pause the video and try that on your own, although of course you don't have to. If I were trying to come up with this curve, what I would do is probably follow the method that I did in the previous example. I track the time, the corresponding x-coordinate, and the corresponding y-coordinate. And you could pick whatever you want for the values of t, but maybe -2, -1, 0, 1, and 2 would be enough of a range of values that would give us a pretty good idea of what the graph looks like. Plugging those values into this top equation, -2 squared is 4, and 4 minus 2 is 2. -1 squared is 1, and 1 minus 2 is -1. 0 squared is 0, 0 minus -2 is -2. 1 squared is 1, 1 minus 2 is -1. And 2 squared is 4, 4 minus 2 leaves me with 2. To figure out the corresponding y-coordinates, I plug them into this equation. 5 minus 3 times -2 is 5 minus 6, which is 11. 5 minus 3 times -1 is 5 minus -3, which is 8. 5 minus 3 times 0 is 5 minus 0, which is 5. 5 minus 3 times 1, 5 minus 3 leaves me with 2. And 5 minus 3 times 2 is 5 minus 6, which is -1. I don't think all these points will fit on the axes that I have pictured, but I could probably get enough to get an idea of what's going on. Let's see, at time 0, the x-coordinate is -2 and the y-coordinate is 5. So here's -2 and here's 5. This is where time is equal to 0. At time 1, x is -1 as y is 2. Here's -1, here's 2, here's time 1. At time 2, the x-coordinate is 2 and the y-coordinate is -1. Here's 2, here's -1, this is time 2. I don't have room for any of these other points, but maybe I can kind of get an idea. At time -1, the x-coordinate should be -1 and the y-coordinate should be 8. So somewhere loosely speaking up here, just off of my graph, is where t is equal to -1. And maybe I can tack on one additional point here at time 3. At time 3, the x-coordinate would be 9 minus 2, in other words, 7. And the y-coordinate be 5 minus 9, in other words, -4. 7 is a little off my axis, somewhere over here. -4 is somewhere down here. This dot somewhere out here is where time is equal to 3. What's going on here is if you want to think about time 0 as kind of the start, this particle starts over here and it's moving not super fast, but it starts moving faster and faster as we go in this direction, as it continues down like this. How do I know it's moving faster? Because look, for the first, I don't know, second maybe, it only travels this far, but the second it travels further, and the third second it travels even further. So we're kind of speeding up as we sling around this corner. And if we want to kind of travel back in time, at time -1 it was up here, sort of heading down in this direction. And maybe you can get an idea, taking advantage of symmetry, that at time -2 it would have been somewhere up here. It's moving pretty quick as it slings around here. It slows down as it goes around the corner, speeds back up, and heads out in this direction. These parameterized equations represent this curve that's shown in purple. And unlike the curve in blue, where the particle is kind of traveling at a constant speed, these time intervals are equally spread out. For the curve in purple, we kind of get some idea of speed, which is something pretty cool that comes out of parameterized equations. Really, the purpose of this video was just to introduce parameterized equations. And if you're at the point where I can give you parameterized equations and you come up with the graph, you've learned everything you're supposed to learn in this video.